Hi everybody. This is just a really short video describing how to use English units for ideal gas problems. And the problem that I'm going to use as an example is in your textbook, Chapter 8, Problem 67. So in Problem 67, what we have is an evacuated 40 cubic foot tank connected by a valve to an airline, and the pressure in the airline is kept at 150 psia and a temperature of 90 degrees. So the problem goes on to ask about work potential or usable work of the air. But the first stumbling block that you hit is just trying to determine how much mass of air moves from the supply line through the valve into the tank. So the first thing we do is we set up sort of a continuity equation where we say that since there's zero mass in the tank, we're told it's evacuated, that all of the mass that's in the tank at time 2 is due to the mass of the air that comes into the tank. So we can just say that the mass that comes in is equal to the mass final because the mass at time 1 is equal to 0. When we're talking about getting work potential, we also need to know the ambient temperature T sub 0 of 80 degrees Fahrenheit. But in the meantime, we just have to calculate what this mass is. So since this is air, we don't have really good tables. And the assumption I made was that we could use the ideal gas law, and that the air behaved ideally enough that we could make that assumption. So we start with PV equals MRT. And to find for the final state, mass at the final state, we can say the P of the final state in the tank, which is 150 psi, times the volume, which is 40 cubic feet, divided by the gas constant for air, not the universal gas constant, but the constant for air, divided again by the temperature, is equal to the final mass in the tank. Now when we set this up, we have 150 psia, 40 cubic feet. Then we have to take the temperature in the tank, 90 degrees Fahrenheit, and add 460 to convert to degrees Rankine. And then we need a value of the universal gas constant, or in this case, the particular gas constant that will make those units work. So where did I find this value? Well, if you go back to either your textbook or you go back to our Moodle page, I have placed here the thermodynamic property tables in both English and SI units. Appendix 1 of the tables gives us SI units, which are not particularly useful to us at this point because we really have to get to the point where we have those English units. So if we start here at table Appendix 2, you'll see that Appendix 2 gives us the values of English units. And the first table, A1E, which in your textbook is a little bit different, but it's page 960 on this PDF file. It's 9 something else, I can't remember. It's still in the 900s, but the table is A1E, and you see that we have the heading is that this is the molar mass, gas constant, and critical point properties of different substances. So the first substance is air, and we have a molar mass. Then we have a gas constant, R. We have it in, there are two different values. One of them is BTUs per pound mass degree R. The other is in PSIA, cubic feet, pound mass degree Rankine. Well, if you recall, the problem that we have gives us the pressure in PSIA, the volume in cubic feet, and the temperature in degrees Rankine. So we can work with that value of 0.3704 psia cubic feet pound mass degree Rankine. And if we use that value, we see that psia cancels out, cubic feet cancels out, degree Rankine cancel out, and we're left with pounds of mass in the denominator of the denominator, which of course flips to the numerator. And we get a value of 29.45 pounds of mass. Now, this actually has a little bit too many significant figures, but when you carry it over to the next part of the problem, I think it's okay to leave it at 29.45. Just make sure that your final answer is expressed in the proper number of significant figures. All right, so that's it. Please let me know if you have any questions, and we'll move forward from here.